Hi, I'm going to talk you through the example in the textbook 2.34, how to calculate the amount of energy released by a particular mass of fuel, because I'd like you to do it in a different way to the textbook, a little bit different. So the question is calculate the energy released in kilojoules, although it doesn't say what units it wants your answer in, when 3.6 kilograms of butane is burnt in an unlimited supply of oxygen. So this particular example doesn't have any change in enthalpy here. So if you're not given the change in enthalpy, then you need to look in the data booklet. Okay, so in the data booklet, page 10, there's a whole lot of fuels. And in the past they used to just give the kilojoules for every mole. In the data booklet, when it says kilojoules per mole for this example here, this actually does mean for 1 mole. But now, instead of, if you've got a certain number of grams, you would in the past have to have turned it into moles before you could have used this. Now they've given you kilojoules per gram. So this is how many kilojoules for every 1 gram of fuel that you're burning. So we can use these values. The data booklets, this information up here, they keep changing it. So they went through about 3 different data booklets last year, because when it's at standard laboratory conditions, they had written in here that the water produced would have been a liquid. So in the past, when we did combustion reactions, you always had to have the states of carbon dioxide and water as gases. But then when they introduced this, apparently at these conditions, the water is written as a liquid. And now apparently they've decided that they'll just leave it off. So I'm not sure exactly, and I'll have to have a look to see whether it should be a gas or a liquid when you write combustion reactions. Okay, so if we have a look, we had butane, so we're using this one, and because we've got our information in grams, we can just use the 49.7 kilojoules for every 1 gram of fuel. Okay, so if we have a look at our question, we have our information as how many kilojoules per gram, but the question is asked has the information as kilograms, so we need to convert the kilograms to grams. Kilograms are a larger unit. There's 1 kilogram for every 1,000 grams, so you're going to need to multiply it by 1,000. So the reason I'm doing this video is because I don't want you to use the equation in the textbook. That equation is just a rearranged ratio, and if you use that equation as it is, the number of moles, or if you just have grams, it won't work sometimes, because if you're getting the change in enthalpy from the data booklet, the change in enthalpy in the data booklet is for every 1 mole. Whereas if you get the change in enthalpy from a thermochemical equation, then that kilojoules would be however that's written, and if it was for this one, it would be for 2 moles. So your data booklet value would be doubled. And this equation only works if it's for 1 mole. So don't use this equation, just do a ratio. Just with all our ratios, we're putting what we want on the top. We want to know the kilojoules for 3,600 grams, and the relationship that we know, the kilojoules, we know that there's 49.7 kilojoules for every 1 gram. So then you just rearrange it as we normally do. Take this over the other side, multiply it. You can see in Edrolo, Catherine doesn't tend to write the units, but the units really tell you what to do. If you put the units in, you can't go wrong. When you take this, it's divided on that side, you take it over the other side, put it on the top when it's on the bottom, and the units will just cancel out and you see you're left with kilojoules. So really it's so much easier just to use ratios. When you multiply it, you get 178,920 kilojoules. Don't leave it as that. Look here, you've got 3 significant figures, so your answer has to be in 3 significant figures. So because this is a larger number than 3 significant figures, there's a few ways you can get 3. You could convert this kilojoules to megajoules, make it 1,000, a unit that's 1,000 times larger, which would mean you would have 1,000 less of these. So you would divide it by 1,000, and then move the decimal place to here, so you would get 178.9, so you round it up to 179 megajoules. So that gives you 3 significant figures. The other way of doing it is to turn this number into standard notation and only quote 3 numbers. I've never seen a question where they gave you a significant figure, a question where they expected you would get marks for significant figures, where they gave you a number that you had to turn into standard notation in order to achieve that. So they would probably say up here in the question, quote your answer in megajoules. So you would get 1 mark for turning this into megajoules, and then they would give you another mark for turning it into the correct number of significant figures. Okay.